While I'm waiting for an AliExpress order to arrive, I thought I'd have a play with some logic gates. As a means of testing logic gates, I've built this circuit. The circuit diagram for what is shown here can be seen on the screen now. It's fairly straightforward. Basically, we have a gate of various different sorts and an LED attached to the output. There are two buttons. Let's call them button A and button B. These buttons control the logic levels applied to the gate inputs. The input signals for all the gates are pulled low through two pull down resistors. When either button is pressed, that input is then pulled high to the voltage rail. Starting from the left, we have an inverter or a NOT gate, an AND gate, an OR gate, an XOR gate, a NAND gate, a NOR gate, and a XNOR gate. This one has a little resistor coming down, and I will talk about that in a little bit. On the output, they all have LEDs. I'm cheating a little bit because all the LEDs share a single resistor to limit the current. Now we've powered it up, let's go through all the gates and see what happens. If we start with the NOT gate inverter, if I bring up the truth table, we can see what it's supposed to do. You can see at the top here-ish that the symbol for the NOT gate is a triangle with a little round nose on the end. It has one input that you can see here and one output. There is a yellow wire here for the input, which is connected to the A button, and that is the only input to the inverter in here. The output of the inverter is the opposite logic level to the input. If the input is high, i.e. it's a logic 1, the output will be low. In this case, the input is low and therefore the output is high and the LED is on because the button isn't pressed. And this resistor here is pulling down the signal to ground or low. Because it's low, the LED is on because the signal coming out of the inverter is high. It's inverted. And if I press the button, the A button, the LED should go off. Let's try that. I can press the B button as many times as I like and it doesn't affect the output there, which is what you'd expect, since it's not actually connected to the inverter. If I press the A button, that brings the signal to the input of the inverter high, which means the output is low and the LED goes off. The next chip on the list is the AND gate, which is this one here. And if I bring up the truth table for the AND gate, you can see the symbol here above, and it's basically a sort of oblong square with a rounded semicircle side, and you can note that it's got two inputs. And you can see those inputs are connected to the A and B buttons by the yellow and white wires. Yellow is input A and white is input B. Looking at the truth table, if both inputs A and B, the yellow and white wires, are low, the output will be low and the light is off. If the yellow wire A input is high and the white wire B input is low, the LED remains off. If we reverse those two so that the yellow wire, A wire, is low and the B wire, the white wire, is high, the light remains off still. The final entry in the truth table is when both the A input and the B input are high. When this happens, the LED should come on because A and B are high. Let's press the buttons to see what happens. Just pressing A on its own and the LED doesn't come on. If I press B on its own, the light doesn't come on. If I press them both down at the same time, the light comes on. That means there's a high on the output of the AND gate. It only occurs when A and B are high. The third gate is an OR gate, and you can see it here. The truth table for the OR gate looks like this. The schematic symbol for the OR gate is a pointy, more aerodynamic version of the AND gate. And again, in this case, it has two inputs. On the truth table, we can see that if both the inputs are low, then the output will be low. And that's the state it's in at the moment. If either the yellow or white, that's the A or the B signals, are high, then the light should come on. Or if they're both high, the output will be high and the light will come on. The only state where the light remains off is when both A and B is low. So to test this, if I just press A, the light should come on. And it does. If I just press B, it should come on. And it does. If I press them both down together, it should come on. And it does. The fourth chip along is an XOR gate, or exclusive OR. What the exclusive OR gate does is the output will be high if either the A or B signal is high, but not if both signals are high, as can be seen in the truth table here. The schematic symbol for the XOR gate is the same as the OR gate, only we have this little bar at the back to indicate that the inputs have to be exclusive. So to test it now, if I just press the A button, the light should come on. And it does. If I press the B button, the light should come on. And that does too. And if I press them both together, the light should remain off. Which it does too. Unlike the LED to the left, which is the OR gate, which doesn't exclude an output, a high output, when both inputs are high. The fifth chip along is a NAND gate. That is a negative AND gate. From the truth table we can see that the output is high unless both A and B are high, in which case the output is low. So we can see at the moment, as both buttons are not pressed, A and B are low and therefore the light is on. If I press A on its own, the light remains on. If I press B on its own, the light remains on. If I press them both together, the light goes off. Yay! The symbol for the NAND gate is the same as an AND gate, only it has the inverting nose on the end of it to indicate that the output is inverted. Or to put it another way, it's taking A and B as inputs and then inverting the output, which is what we see on the truth table. We could do the same thing if we wanted to by taking A and B through an AND gate and taking the output of the AND gate and putting it through the inverter or the NOT gate in the chip on the end here. And that is how the NAND gate appears to function. It doesn't quite function like that, but I'm not going to go into that just yet. The next one along is the NOR gate. So that's the NOT OR gate. And as one might imagine, if I bring up the truth table, it does the opposite of an OR gate. And in this case, we can see that the output is high, and so the light will be on if both the inputs A and B are low, and for any other combination of inputs the output is low and the light will be off. So let's demonstrate. At the moment both buttons are not pressed and so the light is on. If I press the A button, the light will go off, and there it is. If I press the B button, the light will go off, and it does. And if I press them both together, the light will go off, and it does. So again, we can see that as with the NAND and AND gates, the NOR gate is basically doing an inverted version of the OR gate. And if we look at the little symbol up here, we can see that that is what the symbol is. It is an OR gate with the little nose on the end to indicate that the output is being inverted. The final chip on the board is an exclusive NOR gate. So that's an XNOR or exclusive inverted OR gate. And at this point we can probably guess what the truth table looks like, but here it is anyway. Essentially, if one or other of the inputs is high, the output will be low. Otherwise, the output is high. The symbol is again not surprising. It is essentially an XOR gate with a little nose indicating that the output is inverted. Let's try this then. At the moment both inputs are low and therefore the output is high and the light is on. If I press the A button, the light goes off. If I press the B button, the light goes off. And if I press both buttons together, the light remains on. Now, you might be wondering why this one has a resistor connecting to the output, whereas all the others don't. The reason for that is because this is a special, shall we call it, type of gate which has something that is called an open drain, or in other technologies you might call it an open collector. That means internally it doesn't have a pull-up resistor on the outputs, and so one has to be added. If I were to disconnect the pull-up resistor I've got here, the drain of the output transistor would not be connected to anything and therefore would be floating. So with open collector and open drain logic gates, you have to have some form of pull-up resistor. We can string together lots of different logic gates into an array of logic gates that produce a certain output with certain inputs. This is called combinational logic, and while I'm not going to do it in this video, I did want to demonstrate a different sort of logic using these gates where the logic gates will remember what information they've been told. To do this, we can use latches and we can use flip-flops. In this case, I wanted to build a latch, and this is the simplest kind of latch. It's a set reset latch. The set reset latch, as we can see from the diagram, has two inputs, set and reset, and two outputs, Q and not Q. When we apply logic high to the set line, this causes Q to go high and not Q to go low. If we then take the set line low again, the Q output remains high, and it shouldn't matter how many times we then place a signal on the set line, the Q output remains high. It's not until we apply a high signal to the reset line that Q will revert to the zero state. We can demonstrate this on this board. I've wired up a couple of NAND gates as per the diagram to demonstrate it. Now, because the set reset latch requires low signals to activate set and reset, I've wired the outputs from the switches, which are active high, through two inverters on the NOT gate package on the end here. In other words, when the buttons are not pressed and the signal at the button end is low, when it comes out of the inverter the signal is high, and vice versa. If I now press the set button, the light comes on. When I release the set button, the light remains on, and it doesn't matter how many times I now press the set button, the light remains on. If I now press the reset button, which then puts a high on the white wire, and the light goes out, and it stays low once I let go of the reset button. And again, I can press the reset button as many times as I like and the light does not come back on. And again, if I press the set button, the light comes on. When I release the set button, it doesn't go off. If I press the reset button, the light goes off. That's latching. This circuit as it stands, however, does have one weak spot. If I press both buttons at the same time, the output state is indeterminate. That means we can't know what it will be when we stop pressing the buttons. In this case, the determining factor is probably which button, the set or reset, is released last, if that makes sense, because you're never going to be able to get both buttons to be depressed at the same time and at the same speed. However, in a more sophisticated circuit, you would still not be able to predict what the output would be after applying a signal to both the reset and the set. Ideally, with a set reset latch, you want to prevent set and reset from being active at the same time. One way to do this is with a mechanical interlock. That is, having some form of mechanical switch that prevents both signals being active simultaneously. In this case, I'm using a momentary rocker switch with 3 positions. In the one position, the set is active. In the other position, reset is active, and in the neutral position neither is active. So here, when Q is high and the LED is on, if I press the reset direction on the rocker switch, the LED goes off. If I then press the set button or the set direction on the rocker switch, the output will go high and the LED will come back on again. And because the rocker switch prevents both the set and reset from being active simultaneously, I cannot enter the intermediate state, and therefore I always know whether or not I'm going to get a set or a reset output.